This section of the notes looks now at the basic components, optical components that you'll find inside a laser. So if you were to open the box, what would you find inside? Now, we're not going to go into everything that you might find inside a laser, but just some of the more common components. Okay, so we'll start with a basic description. We've already seen how we can get gain from a particular material, and that we get stimulated emission, which gives us lots and lots of gain. And the secret of success for the laser is that that gain has to be fed back into the system. So in other words, that we make a positive feedback loop. So that feedback loop is shown schematically here in figure, whatever it is, 12. So that we have our laser material. This is our laser material here, and that's what's going to give us the gain. We have our energy source coming in, so this is however we're providing the energy by passing a current through the gas, or using a flash lamp to put photons in, or whatever. So energy in, positive net gain, and we take our output signal from there. But to close the loop, we then close it as a positive feedback loop. We then feed that back in to our gain system. And the way that we do that with an optical system is just by using mirrors. So the energy source might come from, for example, if this was a ruby rod, then you might use a flash lamp here. So just a white flash lamp, and that flash lamp, top and bottom, will give you a burst of energy, a pulse of energy, which will be absorbed by the ruby, and that's how we pump our laser. That's how we get the atoms up into energy level 2. We'll then start seeing bits of spontaneous emission, sort of going off in all directions. But a tiny amount of that spontaneous emission will be heading towards the mirror, and if the conditions are right, then that light will start to bounce backwards and forwards and get amplified every single time it passes through the laser rod. Every time it passes through, getting a gain, more and more gain. So the basic bits of the laser is we need an input energy source. We need some material which is going to give us the gain, and we need some way of making a feedback loop. Okay. Now, what we've not mentioned here is the input signal X. That input signal can be an external source, so you might use another laser to start the lasing within a material, so that the main laser acts as essentially as a power amplifier for your weak input signal. That's referred to as injection seeding, but one of the things that should be apparent here is that even with small amounts of stimulated emission, if the spontaneous emission, I do apologise, spontaneous emission, if it satisfies the condition of resonance between these two mirrors, in other words, if we're getting bouncing backwards and forwards between those two mirrors, then we close the feedback. If the light's going off at some direction like that, then we're not going to get any feedback, so that's energy which is lost. Okay. So we need a laser material. We need some positive gain, net gain. So if we take all the losses and all the gain, we subtract one from the other, then the net gain should be positive. The output is fed back in to the system, and with positive feedback we get an exponential growth of our signal. The maximum that we can extract from that system will depend on how much energy we put in, and also obviously depends on the amount of loss within the system. So input energy and system losses will determine just exactly how much power or energy we can get from the laser. So for a working laser, we need a working laser system. We need some laser material, we need an energy source, and we need feedback. Now the feedback referred to there, just using just two mirrors as the simplest example. These mirrors form what's called a laser cavity. Let's think about that in a little bit more detail. So here's badly drawn mirror 1 and badly drawn mirror 2. And somewhere in here is the laser material. And this space in between these two mirrors is referred to as the laser cavity. Okay. And that cavity can be in resonance. And the way that it's in resonance is that if we have a standing wave, then that will be a resonance condition. So in other words, if the length of the laser cavity is equal to some integer, let's call that small m, times the wavelength, then we can have a standing wave, and that standing wave will then give us resonance within that cavity. If we don't have that condition, if it's not a standing wave, then the light which is being reflected will be out of phase with any light coming in, and you will get cancellation. Maybe not 100% cancellation, but you will get loss. And as we've seen, any positive feedback loop, even the tiniest bit of advantage of one part of the system over another, so one wavelength compared to another, means that because of the exponential growth, you get all of the energy being deposited into this resonance condition and not into a non-resonant mode. So that can be any integer times. I'll try and draw lots and lots of waves. Any integer times the wavelength. That's how we get our resonance condition. So the laser cavity has its own resonance condition, and we've seen that the laser material has its own choice of wavelengths and frequencies. So we'll see in a second just how those work together to give us the laser output. The input signal I've mentioned, there's none shown in the figure of the laser system, and that's because what we use as our initial starting point, our seed point, is the spontaneous emission, which happens to be travelling in the right direction. In other words, we start from noise in the same way that if you're at some karaoke night and you take the microphone, you put it up against the speaker, you get this enormous squeal, then that's exactly the same thing. It starts from tiny little noise levels, and then suddenly positive feedback, you get a massive amplification at one particular frequency. Okay. The gain inside the cavity, in other words, the amount of light which is being produced, is usually so high that we don't need an external input signal to get it going. The ones which are giving you the maximum gain, the maximum or the minimum loss, will be the ones that are amplified. As I say, you can use an external source if you like, and that's referred to as injection seeding, using maybe a small laser diode to seed the output from a much more powerful laser, so you can get essentially, as I say, just working as a power amplifier. So we've got the gain of the laser material, which is frequency dependent. We've got the feedback mechanism, which is also frequency dependent. And so we have to have the cavity designed in order to make sure that those frequencies work together. The frequency that the laser material likes to work at and the frequency that the laser cavity likes to work at, we need to make sure that those are matched in some way. Okay. The resonance in the cavity, referred to as the modes, longitudinal modes, standing waves inside the gain spectrum, that will follow the integer times the wavelength. So the separation between those two mirrors has to be m times lambda. And because the system, the laser cavity, is in resonance, then we refer to the whole system with the laser gain material inside as the laser resonator. There might be lots of frequencies which could possibly work within the laser. The laser material might have such a range of different frequencies that there could be a whole range of different outputs possible from the laser. I'll show you that in this diagram here. So let's supposing this is the frequency response, if you like, of the laser material. And this is the frequency response of the laser cavity. Then, for the material, any of these frequencies in this curve, when it's above, when the gain is bigger than the loss, in other words, we have positive net gain. So when the gain is bigger than 1, so I think up in the diagram up the top there, I called it K. K is greater than 1. Then all these frequencies could actually work as our laser. So which ones are going to work? Well, that depends on the behaviour of the laser cavity. So here's our L equals n plus 1 response. So this is the frequency again, and this is the resonance of the transmission, if you like, of the two mirrors, the simple two mirror system. Here's m plus 1 times lambda, m plus 2 times lambda, m plus 3 times lambda, and so on and so on. M minus 1, m minus 2, and so on. So what we have is that we've got all of these potential frequencies where the resonator can work. And you'll see that these are a series of very narrow frequencies. And then we've got the range of frequencies over which the laser material can work. And so when we combine them, when we do an A plus B, then what we get is the output from the laser, which might look like this. So that's the combination, of the material and the cavity together. So what we have here is we've got essentially we've got 1, 2, 3 modes output. So that's referred to as a multi-mode laser, and that's multi-longitudinal modes. Dr. Watson, I think, will talk to you about transverse modes, TEM and so on. The laser is multi-mode because it exhibits many longitudinal modes, so in the case down below 3. If you could get the resonance narrow enough, or the spacing between the resonances wide enough, then you would only have one single mode which could operate, and that then is referred to as a single mode laser. And there's lots of applications where having single mode is useful because you have a much narrower range of frequencies coming out of the laser. Lots of applications which benefit from that.